I want to talk about computational complexity theory, which is my research area. It's also the area in which Arvind works, and how this, what research in this area has been happening at IMSc through the decades. But of course, I cannot talk about all the work that happened here, and so I will just pick a few things here and there to highlight, and I want to put this in the context of computational complexity research that was happening worldwide. So what was happening elsewhere in the world and what was happening in IMSc at the same time. So to start, to go to the very beginnings of computational complexity, this is, let's look at a computing world even before 1965. So that was a time when computing devices had, they had become a reality. There were real computers. They had been used in some form for breaking codes during the World War and so on. So then by then there was already this need for some kind of abstraction, abstract formalisms to reason about these machines. Turing machines, as a study, as an abstract computation model, the Turing machines had already been around for a while. And recursion theory, which was in the domain of mathematics, already a lot of stuff in recursion theory had been done in the context of Turing machines and computability. So we already knew that there are problems which are not solvable by any Turing machine, and we knew that there are, even for problems which are not solvable or not decidable, there are degrees of undecidability. So this was the state kind of before 1965. And then around that time, so incidentally that was also the year when I was born, so it was a nice year to pitch this. And in the mid 60s, this was electronic universal computers, they had really become a reality, and it became a more pressing concern to talk about not just what is computable and what is not computable, but about what is efficiently computable and what is not efficiently computable. What is efficient enough? This question itself required some attention to be able to describe formally. So here is a very brief list of landmark results which happened in the early years of computational complexity. So these years, 1965 to 1980, one could think of as really laying the groundwork for this research area. So this is well before computational complexity started in IMSc, but just to get the background for what was happening. So the notion of what is efficient, this was actually formalized first by Cobham and Edmonds in 64 and 65 in the context of Edmonds in particular was talking about algorithms for finding matchings, pairing up nodes in a graph perfectly, and he was looking for a notion of when would this algorithm be good enough, and he came up with polynomial time as the answer. So then following up on that, Hartmanis and Stearns had this very influential paper which defined the complexity classes as we talk about them today. What can be solved in deterministic time t, what can be solved in non-deterministic space s, and so on. And a whole lot of results about these kind of resource bounded computations came about them. And then here we had what is pretty much the, like the poster boy question of complexity theory, is P equal to NP. So this whole notion of NP completeness was proposed by Cook and Levin in 71 and 73 on two sides of the Iron Curtain, and Richard Karp also described a whole lot of combinatorial problems which are also NP complete, and that started off a flurry of work in this. This flurry of work was very different from what would have come directly from recursion theory, but at the same time many structural results were being explored in this decade as well as in the next decade, which were driven by recursive function theory. So in recursion theory, you know about degrees of undecidability. What is the analog here if you are talking about tractability? Are there degrees of intractability? Okay, this problem is NP hard, it's very hard to solve. If I give you magically a way of solving this, then does something else still remain hard, or does it become easy? So these were notions which came from recursion theory, and we were looking at them in this context of resource bounded computation. Then towards the end of this decade, Valiant started looking at the complexity of counting, which is very different from just checking whether there is a solution to some problem. You want to know how many distinct solutions there are. At the same time, at the end of the decade, Cook and Rekhau proposed this notion of proof systems, trying to look at automated theorem proving procedures. What is the syntax in which one can write a proof so that a fairly dumb system can check that proof and certify that it is correct or it is not correct? Okay. And this last result here is actually an algorithmic result, not really a complexity theory result. Linear programming was shown to be in P. The reason why it is here on this slide at all is that at the time when P and P were proposed as these major central classes to look at, very soon after that it became clear that almost all natural problems are complete for some class or the other. So therefore our notion of what is a complexity class is fairly robust, and also that there are very few problems that seem to be in between P and NP. I mean, we don't know that they are in P, but we don't know that they are the hardest problems in NP, that they are NP complete. Linear programming was one of those, and by the end of the decade already it was known that it was in P. There were a few others which will show up a little later in this talk. So this was happening in the period 65 to 80. As I said, this period laid the groundwork for the research area of computational complexity. What happened in the next decade? So the next decade was actually very exciting. Most of the research in this decade was focusing on understanding different modes of computation. What can you do with non-determinism? What can you do with alternation? How do you model parallel computation? I mean, the Turing machine is some kind of a sequential machine, but you want to understand parallelism. What does randomization mean in this context? What about interaction between a prover and a verifier? So a whole lot of results around these kind of modes of computation. The excitement that I refer to came from these 2 points. So in the 80s, we got our first non-trivial lower bounds. So the situation in complexity theory as opposed to in recursion theory, which I alluded to before, is that we already knew that almost all functions are very, very hard. A completely straightforward counting argument tells us that, if you are going to look at only polynomial time, there are very few algorithms that can run in polynomial time. There are way too many problems. So obviously the number of problems that is hard is huge. As a mathematician, the problem is solved. There exist problems which are hard. As a computer scientist, we want to know what are those problems which are hard. And since most of them are hard, this is not a question of finding a needle in the haystack. It is a question of finding hay in the haystack. There's just hay everywhere. And you want to put in your hand into this thing blindfold and pull out a blade of hay, and this seemed incredibly hard. So it's very counterintuitive, but that is the situation. This is the situation even now. So the first explicit lower bounds that we had, an explicit function which we know cannot be computed by a polynomial size circuit, albeit a circuit of a specific restricted type, a constant depth circuit. So this was a very simple function. Given an n-bit string of zeros and ones, is the number of ones in it odd? As simple a function as that. If you are allowed only a circuit with AND, OR and NOT gates, and a circuit which has only a constant depth, maybe depth 10 or 15 or something like that, then the number of gates you need is going to be exponential, 2 raised to n raised to something. Okay? So this was a really major breakthrough. For constant depth circuits, we have exponential lower bounds. Another breakthrough around the same time was for monotone circuits, circuits which do not even use the negation gates. Well, they cannot compute all functions, but amongst the functions that they can compute, does that negation gate help? So here again we got exponential lower bounds. So this was a very inspiring and exciting time to be. Proof complexity lower bounds came in also in the same period. So this 85, 86, an incredibly rich period for us. Haken was able to show that this extremely simple statement which says that you cannot put, say, 101 boxes into 100 bins without having at least one bin which has 2 boxes in it. So this is a self-evident statement, but if you want to write down a proof of it in a specific syntax, a syntax which is used by most common algorithms today to solve the satisfiability problem, then what Haken showed was that such a proof will have to be just way too long. Okay? So these were the really exciting lower bound proofs, and the goal of complexity theory is to prove these lower bounds. So it looked like we were making progress. There were also some very surprising upper bounds, things that you can do within a limited amount of resource which we expected could not be done. So there were these few major results by Barrington, by Immerman, Selepseny, showing unexpected power of certain modes of computation. There was this result at the end of the decade by Toda which showed that counting is, the Valiant had proposed counting as another thing that you should look at, not just checking for the existence of solutions, but counting how many solutions there are. He showed that this is a much harder problem. It's much harder than non-determinism, it is harder than even alternation, and so on. And then there was this notion of interactive proofs. I have briefly mentioned here interaction. What can a verifier convince himself or herself about if the verifier is also allowed to talk to a prover and ask questions along the way and is allowed to use some kind of randomness. So interactive proofs also revealed unexpected power. It looked like it was shown that with interactive proofs you can actually certify any problem which can be solved in polynomial space, a much larger class than NP. So these were some surprising results in this decade. There were many other results, but I've just pulled out a few here. Okay, so what was happening? What else was happening in this decade? Well, it was in the middle of this decade in 1986 that the first conference on complexity theory started worldwide. So it was called Structure and Complexity Theory, and it's been an annual conference since then. So leading papers in this area are published in this conference, announced to the world in this conference. It was also in this decade that the first seminar course on complexity theory was offered at IMSc. This was I think it was in the Feb semester of 1988. Arvind was a faculty member at IIT Madras. I was a PhD student there. And the computer science group here was a very small group. There was Tyagarajan, there was Ramanujan, there was Kamal. And they knew about these exciting things happening in complexity theory elsewhere, and they wanted to hear more about it. and next door was this complexity theorist. As far as I know, Arvind was the first complexity theorist to do a PhD in complexity theory in India. Am I right? I don't know any other complexity theorist who has done a PhD here before you. So Arvind came over and to IMSc and gave this course, and I also was coming over and attending it. That's how I got interested in complexity theory. So this is what was happening in IMSc in complexity theory at that time. Okay, so still not much because we are trying to learn what's happening. So let's move to the next decade. So the turn of the century, 1990 to 2000, many interesting developments across the world. Well, probabilistically checkable proofs came about. This is a new format, a format in which you can write a proof so that a verifier need not even look at the whole proof. A verifier can use randomness and decide to check maybe some 100 lines of the proof. The proof may be 1,000 lines long, 10,000 lines, doesn't matter how many. The verifier will only look at 100 lines, but randomly. And with high probability, the verifier can be convinced that the proof is correct. So this notion itself was so counterintuitive. It made a big splash. There were articles in New York Times. At that time, there wasn't the blogosphere. Had there been the blogosphere, it would have been, so to say, viral in the blogosphere. But it did make a big splash. So this was one very exciting thing at that time. There were new links coming up between communication complexity and circuit depth. So now we keep hearing about Alice and Bob talking to each other and trying to compute a function. And many exciting results about this came at that time. Hardness, randomness, cryptographic assumptions. Major results in this field came about again in this decade, 1993-94. There were some very influential papers by Nissan and Vigdeson, which said that you can turn around pseudo randomness and construct hard functions. If you have functions which are hard, you can use them to get rid of randomness in algorithms and so on. So it was around this time that finally people realized that, well, there was the name of this conference, Structure in Complexity Theory, because we were looking at structural results, how these complexity classes relate to each other via reductions, notions of comparing problems. And there was a lot more which was happening in complexity theory, which is not quite adequately represented by this word structure. So the conference got renamed Conference on Computational Complexity, which is what it is known even now. So against this backdrop, now things started happening in IMSc. People at IMSc, these three people, Vinay joined in January 1993. He was here for less than a year, but I think his presence here was quite important. Arvind joined in March or April, May. No, you were in April. I looked up the annual report for that year. It says you joined in April. I see, maybe May. I joined in April 1994, but I was already here in 93 as a postdoc. So there were suddenly 3 complexity theorists in IMSc. There were more people interested in, there were complexity theorists as well as people interested in complexity theory in Chennai at CMI, which was then SPIC School of Math. Manendra was there, Milind Soni was there, KV Subramaniam was there, so we were all talking together. So in 1993, for the first time, a course on complexity theory was offered on credit. And this was such an experimental course, I tell you. There were 4 of us who were jointly teaching the course. We decided we all wanted a finger in this pie. Exciting things happening, we are going to teach the students. Manendra, Arvind, Vinay and myself, all of us took turns teaching. And I think we thoroughly confused the students, but nonetheless, one of them did go on to do a PhD in complexity theory. So maybe not all was lost. In August to November 94, we had a seminar course on the polynomial method in circuit complexity. And this was because there had been some of the exciting results that I talked about earlier actually used algebraic methods to talk about something essentially Boolean, to talk about Boolean complexity classes and relations amongst them. So this seemed something very exciting. We wanted to understand it better, and we organized a workshop in IMSc in December 1994, and this seminar course was preparatory to that. So this workshop, again, as far as I know, was the first workshop in India on the theme of complexity theory. After that, there have been many such workshops both in Chennai as well as elsewhere, so I won't even list out the rest. But this first workshop happened here, and it required a lot of preparation on our part to be able to appreciate what was going on in that workshop also. Some of the papers that came out from IMSc during this period, I mean, I picked a almost random sample of all the papers that came out then, and of course, I'm not going to talk about all these papers, but just take a look at the titles. So the first one, quasi-linear truth table reductions to p-selective sets. This was in the flavor of the structure and complexity theory kind of work. Okay, so the complexity theory that was being done from 70 to 85. Well, there was work which goes on in that area even today, and in that decade, of course, there was some such work in IMSc also. This second paper here is talking about a new model of computation, and what can you do in this model? You want to understand it better. So you were constantly exploring new models because it is absolutely important that you have the abstract formalisms to reason about and to describe advances that will happen with real world computers. So an exploratory study. Okay, if you are allowed access to resource of a particular form, then what can be solved? Solvable black box group problems. Okay, this is a algebra and computation kind of flavor. So there is an algebraic problem. You're trying to answer something about the efficiency of deciding. So a computational problem in an algebraic setting. And starting from this point, soon after this, maybe it was 2001 or 2002, we first had a full-fledged credit course here on algebra and computation, and after that, I think that course has been very popular. It's an elective course, but every 3 years, maybe sometimes even every 2 years, on demand from the students, Arvind ends up offering the course, and it keeps changing a little bit in character. We are learning more and more about this. So in the very first decade, there was work being done on that place. There is this paper here about depth reduction in non-commutative arithmetic circuits. Arithmetic circuits came from Valiant's program. Let us look at counting, not just decision, but counting. So there is something interesting happening there, and we were trying to explore what more could be done there. As I mentioned, there was a complexity theory thesis also that came out there. It was about counting complexity. It was about computational groups. Okay. Maybe one result from that decade which I would like to highlight, which is of course my own result, and I'm very fond of this result. Here's the title of the paper: Determinant, Combinatorics, Algorithms and Complexity. And what we showed in this paper, this was joint with Vinay, is that we gave a new algorithm for computing the determinant of a matrix. And computing the determinant is something that most computational people would not even think about how it is done. I mean, almost any programming language worth its name will have an inbuilt function which does this, and you just call it. You're not interested in how exactly it's being computed. But we were interested in this because in the landscape of computational complexity, determinant plays a very important role. It is complete for a very naturally defined class, and the fact that it was a member of that class was known earlier via more complicated methods. We were able to give a more direct way of seeing why it is in that class. So stripped of the technical details, what we did was something like this. Given a matrix M, which, to keep things simple, let's say this matrix has just 0, 1 entries. We want to find out what is the determinant of this matrix. From this matrix, we constructed a directed graph G, in which there were these special nodes. There's a special start node, there are 2 special sink nodes, T plus and T minus, such that this property holds. The determinant of M is exactly, so now here is a relation to counting. Count how many paths there are from S to T plus, count how many paths there are from S to T minus, take the difference, that is exactly the determinant. So from the matrix, I can construct a graph which has this property. Well, that's not a big deal. You can just compute the determinant explicitly and then construct a graph which has this property. But what we did was show how to construct this graph from this matrix without actually computing the determinant of that matrix. So the construction of the graph from the matrix was done by an algorithm which used just enough space to hold a constant number of indices, 10, 100, some constant. It doesn't matter how large the matrix is. The matrix may be a 10,000 by 10,000, 2 million by 2 million. I still need to store only 100 indices and have 2 for loops nested one inside the other, and they will end up producing this graph. And this graph has this property. And the way we showed that this graph actually satisfies this constraint, we used a nice, some nice combinatorics over graphs. So in fact, the original paper was titled A Combinatorial Algorithm for the Determinant. And it's only that the later journal version then changed name and became this. So this was what I talked about at the first Institute Seminar Week, which was in 1997. So this whole Institute Seminar Week also started during RR's tenure, and after that we've had it more or less continuously, bar a few years here or there. I did not do anything. Okay. So this determinant paper, in fact, this determinant algorithm, it went on to have a lot of positive effect on other results. For instance, in the very next year, this was used by Eric Allender and some of his co-authors to show an improved bound on the matching problem. Now, this perfect matching problem I mentioned earlier also, pairing up nodes in a graph. That is one of these problems which, as complexity theorists, we are not completely happy about, because it is not characterized properly by one complexity class. So it's in P, it's not complete for P, it's not really complete for any of the standard classes inside P. There is one class which kind of captures it, but it's not completely satisfactory. So even though one may think of designing algorithms for matchings as, you know, in the domain of algorithm designers, not complexity theorists, this problem is interesting to complexity theorists, and many of the algorithms that have been designed for it are algorithms that algorithmists worth their salt will probably not even look at again. So because the algorithms are placing this problem in specific complexity classes. So one such algorithm which improved the upper bound for matching did use this in a very non-trivial way. And there were some other later results which probably I will talk about a little later, which also needed to use this particular determinant algorithm. It was known earlier that determinant computation can be reduced to this kind of computation, but that was via a more obtuse way. This particular way of proving this was also important. So apart from the result, the proof method was something that turned out to be useful in later contexts. Okay, so that was the first decade of complexity theory in IMSc. What happened after that in the new millennium, 2000 to 2010? Many interesting things happened around the world. Again, let me list out just a few of those. Primes is in P was shown in 2002, and like I highlighted the linear programming in P in 1979, there were just a few problems, 3 or 4 interesting natural problems which were in NP, were not known to be NP complete and not known to be P, and one by one those barriers were falling. So linear programming turned out to be in P. In 2002, primes were shown to be in P. A little later in 2004, Reingold showed that undirected reachability is in D log. Now this is a strange result to cite. What it says is, if I give you a graph which could have millions of vertices, so you're not going to be able to look at the entire graph. You're given some representation of the graph as a matrix, and the graph is undirected, so every edge goes in both directions, no one-way streets. Then you want to decide whether it is possible at all to go from some node S to some node T. Well, you can do this using very little space. So this deterministic log space is saying that, so there is a way of figuring out, can I reach T from S by doing a local exploration, the kind of exploration that you do in a maze. Many of you would have heard this method of navigating in a maze. Touch the right, touch the wall on your right with your hand, keep touching this and go all over the maze, never letting your hand let go of the wall. And if you come back to the starting point and you still haven't reached the target along the way, you are probably not going to reach it. Okay? Something like that. At each point, to figure out where you need to go next, you need very little local information. And this is what Reingold showed is possible for any graph, as long as the graph has only two-way streets. If the graph has one-way streets, this breaks down. So an intrinsic difference between one-way and two-way, which till to date we do not know whether that difference is really there. I mean, for all we know, it may also be the case that directed reachability is in D log, and that would be a really breakthrough result. But this itself was also quite a big breakthrough. This area of geometric complexity theory really rose again in this decade. So this was proposed by Ketan Mulmule and Milind Soni. So an approach to solving the big P and P problem by looking at algebraic complexity theory. So a lot of work started in this area at this time, and some of it also at IMSc people did start looking at it. There was this very interesting result by Agrawal and Vinay Kazam at depth 4, which said that if you're looking at arithmetic circuits as opposed to Boolean circuits, it is enough to prove lower bounds for depth 4 circuits. Now this significantly simplifies our task of looking for lower bounds. We want to show that things are hard. We want to show that no possible circuit of this size can compute it. That's a hard task. But now I want to just show that no possible circuit of whatsoever size and depth 4 cannot compute this. Then things are easier. So this, at depth 4, there is a jump between what can be done and what cannot be done. This was a very influential result. And some of the work that happened at IMSc later on did build on this work. So in this decade, there were several PhD theses in complexity theory from IMSc. I've just listed some of the titles, and we don't even want to read out, I mean, this is like a laundry list, but if you just randomly scan this and you look at some of the words here, you know, algebraic problems, permutation groups. So clearly algebra and computation continued to be alive and kicking, okay. Polynomial identity testing. Polynomial identity testing is you are given the representation of a polynomial, you are not given a polynomial explicitly. You are given a polynomial as an implicit representation. Here is a circuit which computes this polynomial. Look at the circuit and figure out whether this polynomial is 0 everywhere. That's the identity testing problem. And it was from the polynomial identity testing problem and attempts to solve it that Manindra and his co-authors had reached the primes in P result. So polynomial identity testing was a big research area. It is still one of those problems which we do not know whether it is in P or no. So there was work about polynomial identity testing. There's more stuff about arithmetic circuits, and then here there is stuff about planar graphs. You can see some stuff about graph isomorphism, and here's commutative and non-commutative domains. Let me pick out a couple of things maybe to highlight. So those were theses from IMSc. Here are papers from IMSc. Again, you can see some suspect words coming again and again. Isomorphism, okay? Commutative and non-commutative computation. So this is in the context of arithmetic circuits. If the product rule is, if multiplication is not commutative, then strange things can happen. It's easier to prove lower bounds, okay? Small space computation, perfect matchings. Like I said, matchings was really a very interesting problem for many different reasons. So matchings is appearing here. The determinant and the permanent, which is the analog of the P and P problem in the arithmetic domain. Planarity testing. So planarity itself, for many graph problems, if the graph is known to be planar, the problem becomes simpler, and we want to understand exactly how this plays a role. So there was work about all these problems happening here. Two results which I would like to highlight, which came out from work in IMSc. So here is this work done by two PhD students at IMSc working with colleagues at IMSc, at CMI and in Germany. They showed that planar graph isomorphism is in log space. So if you are given two graphs, the graphs could be arbitrarily large, but we know that they can be drawn on the plane without crossings. We want to decide whether they are isomorphic. Can you rename the vertices so that one becomes exactly equal to the other? Like these two graphs are isomorphic. So deciding whether two planar graphs are isomorphic can be done again using really tiny amount of space. Just the amount of space required to hold the names of a few nodes, a constant number of nodes. So this was one really amazing result which came out at that time. Another very interesting result which came out towards the end of this decade on the hardness of the non-commutative determinant. So what this result showed was that the determinant we know is easy. In fact, we have known that the determinant is easy for years and years, and as I mentioned in the previous decade, we had even come up with a new algorithm which shows why it is easy. But all those algorithms are crucially using the fact that the product is commutative, xy equals yx, and then you can use that to cancel out unwanted terms. If you want to compute the determinant in the non-commutative setting, then it was not clear that this is easy. And what this paper showed was that, well, in the non-commutative setting, in fact, if the determinant is easy, then in the commutative setting, the permanent becomes easy. And the commutative permanent, that is exactly, the permanent versus the determinant is the P versus NP analog of algebraic complexity theory. So what we are saying is that non-commutative is, it's a big jump. For the problem determinant, which is easy in the commutative case, it becomes very, very hard in the non-commutative case. This paper, in fact, when it came out as a preprint, I remember Avi Vigdason, one of the leading lights in theoretical computer science, he read this preprint even before the conference. He really liked it, and he presented it in the seminar series at Institute of Advanced Studies in Princeton. Okay. Really nice result from that millennium. And then the last decade, the last 10 years. So what was happening around the world? After a long gap, we had another circuit lower bound. So the first lower bounds that I mentioned were in the 85, 86. After that, there was no really exciting circuit lower bound. So what Ryan Williams showed here was that there is an explicit function which cannot be computed by a slightly larger class than the class that was considered in 85. And this explicit function is not even an NP, but it is, at least it is a decidable function. We know what that function is, we can describe it explicitly, and it provably is not computed by small circuits of a particular type. Extension complexity lower bounds came about again in this decade. So what are these extension complexity lower bounds? They are talking about polyhedra in Rn. So you have some polyhedron and you want to know how many facets you require to describe this polyhedron. Maybe some polyhedron requires too many facets. But then you may lift this whole polyhedron to a higher dimension, and suddenly it becomes easier to describe. And if it becomes easier to describe, maybe it does not retain any information about the original problem. So a lifting is useful if its shadow to the smaller dimensions is the original polyhedron. And there was a whole series of papers, fake papers, trying to prove that P equals NP by using the fact that linear programming is in P. Okay, here is this NP complete problem that I want to solve. I will cast it as a linear program, then I will, solve the linear program, and actually I want to show that it is solving the original problem. At one stroke, this entire approach was demolished by Yanakakis in the 90s itself by saying that all those linear programs that you are writing are symmetric, and they actually are large. You are saying that they are small, but those programs are too large. But then he needed the fact that those programs are symmetric, and in this result, then even the symmetry result was eliminated. Now we know that there are concrete polyhedra we know of, which no matter what dimension you lift them to, they will remain hard to describe. Okay? So this was a very exciting development. Graph isomorphism is the third problem. I mentioned these natural problems which are in NP and we don't know whether they are in P. Primes, linear programming fell in 79, primes fell in 2002. Graph isomorphism, we still don't know whether it is in P. But in this decade, now we know that it is almost in P. It's in quasi-polynomial time. So it's like one more bastion falling, so to say. The sensitivity conjecture fell last year. This was something about a conjecture which talks about Boolean functions and their analysis. And this last result, maybe let me spend a couple of minutes talking about this, MIP star. Okay? So I mentioned interactive proofs. So what exactly do we mean by interactive proofs? You think of a verifier trying to check that a proof is correct. And a classical verifier will deterministically check line by line. And only when everything passes, then you say, okay, this proof is fine. So that would be the class P. Then you may talk about randomized, verifier is allowed to use some randomization, and that gives you the class BPP. You may talk about a verifier who is using randomness and the proof is being provided by somebody else. Here is the proof, now you check it using whatever randomness you want. That brings us to Arthur Merlin games, and Arthur Merlin games is something that I think Arvind has done a lot of work on various kinds of games like this. He has given talks in many institute seminar weeks also. Now what if the interaction between the randomized verifier and the prover is allowed to go on over many rounds? It's not just one shot that the prover gives the proof and then the verifier sits and randomly verifies it. The verifier can go back and forth, ask questions, look at the answers, ask the next question. Well, then that is exactly what gives you the class IP, which is equal to P space. That was known in the 89-90, in that decade. It was also known that if the same randomized verifier is allowed to talk to two provers, but those two provers are in two separate rooms, it's like one of these police interrogations. I ask you one question, I ask you another question, but this guy doesn't know what question is being asked there, that guy doesn't know what question is being asked here. Well, if they are telling the truth, it makes no difference. They can do whatever they were doing and they will still pass all tests. If they are cheating, if they are lying, then their ability to successfully con the verifier is hampered by this. So therefore the verifier is able to verify more things successfully. So this multiple interaction with multiple provers was known to be exactly equal to non-deterministic exponential time, which is a much bigger class. But this question was open until 1.5 months ago. If you have a classical verifier, a randomized verifier who is allowed to interact with more than one prover, and those two provers are allowed to not really communicate with each other online, but they are quantum and therefore they can share entanglement, then what can these guys do? What can such a verifier do? So it was not really well understood what such a verifier could do for a long time. Sometime last year it was shown that actually if the provers are entangled, then you can do everything which is in NEXP, in double NEXP time. So that was already, it's clear that giving these provers quantum entanglement adds something more over not allowing them to do that. But now we know that they can in fact do everything that a Turing machine can do. This is the class of recursively enumerable languages. This even includes undecidable languages. So now this is a kind of result which takes us back to the early structural complexity theory kind of thing, that you are back in the domain of recursion theory. There are functions which are not even recursive, which in this model of interactive proofs are suddenly decidable. This is a very exciting happening. This is something that I think, I definitely do not understand what is going on here at all, and maybe in IMSc we have not seen that much of quantum computation to understand this well enough, but it will be nice to be able to see this. Okay, so this was happening around the world. What was happening in IMSc? Here are some of the PhD theses from the last decade. Some new words have appeared here. So we are again, we are not reading out the titles of the thesis, but we are looking at some typical words that have, so the isomorphism continues to appear. You have isomorphism problems for graphs, for Boolean functions. You have arithmetic computations, okay, algebraic complexity classes. These were there in the previous decade and they continued. And then some new things which have come, proofs, okay. So proof complexity for quantified Boolean formulas, verifying proofs in constant depth. This refers to Cook's program from 1979. In what syntax do you write proofs so that an automated theorem prover or a verifier can check these proofs? So let me pull out some papers. Isomorphism continues to be there, black box identity testing continues to be there, algebraic classes both in the non-commutative and the commutative setting continue to figure, and proof systems. If I were to pull out two results that I would like to highlight, here is one result on randomized polynomial time identity testing for non-commutative circuits. So the moment the computation is non-commutative, things are harder for the circuit to do. It is not allowed to flip around variables and cancel things. So the circuit has to put in more work to compute the right polynomial, which means that it should be easier for us to prove a lower bound. Well, we are only trying to prove that this circuit actually evaluates to 0. So it requires more work to prove that. So polynomial identity testing for these circuits is harder. In this paper, these people gave a randomized algorithm which used some very nice ideas. So in particular, it used ideas from automata theory. And this whole notion of using automata theoretic ideas in this context of non-commutative computation was again done by these people. Arvind, Pushkar, and probably Srikant also was involved in that work in the previous decade. And in this paper, they brought together these things. Somehow isolate a monomial in the computation and then check that it indeed exists. So this was one of the, to my view, a high point of some of the papers that came out from IMSc. Another paper which I have listed here, one of my papers is talking about building strategies into QBF proofs. And of course, I don't want to talk about this title itself, but more about the setting. What is it that we are looking at in proof complexity? So the first result that I mentioned, which Haken showed, how do you prove that 101 boxes cannot go into 100 bins without collision if you were to write a proof in a particular syntax, and that particular syntax is resolution. So in resolution, it is very hard to write out a proof of this statement. You require exponentially many lines. But why are we interested in resolution? It turns out that we are interested in this proof syntax or this proof system resolution because current algorithms which actually solve the satisfiability problem, many of them are based on resolution. And it seems a bit counterintuitive. I mean, what do you mean by a current algorithm which solves this problem? This problem is NP complete. There can't be an efficient algorithm for this problem unless P equals NP. Well, we are not saying that this algorithm is efficient. There are lots of algorithm solvers for satisfiability. There is no theoretical proof that they are efficient. That would say that NP is equal to P. But in practice, these algorithms are doing very well. And in fact, the applications of these sort solvers, there are applications in the industrial domain where people are trying to check, is this system indeed safe? Is the system doing what it is supposed to do in many critical systems? The way this verification is done is by writing the expected behavior of the system as some kind of formula and then passing it on to a SAT solver. And that SAT solver algorithm is in principle tackling an NP hard problem. In practice, it is working on instances of that NP hard problem which came from practice like this. And maybe these instances are more structured. The algorithm manages to solve them quite efficiently. So right now, if you ask most practitioners, satisfiability is a solved problem. They are not too worried about P not being known to be equal to NP. And therefore, algorithm designers have become more ambitious. They say, why just satisfiability? Let's try and write algorithms which can solve quantified Boolean formulas. Satisfiability is only NP complete. Quantified Boolean formulas, QBF, is something which is complete for the class P space, a potentially much larger class. And the essential difference between NP and P space is NP characterizes the complexity of one-player games. QBF characterizes the complexity of two-player games. Think Sudoku versus think Go, okay? On larger and larger growing boards. So QBFs, deciding whether a QBF is true or false is a much harder question. Proving lower bound should be easier. But what is the right syntax in which you would write down a proof of this? So in this work, so this whole area of QBF proof complexity is relatively new worldwide, not just here, but worldwide. It's only in the last 10 years or so that stuff has been happening with respect to QBF proof complexity. And here in IMSc, we have also been working on this area and have been trying to design proof systems which can handle QBF formulas and give lower bounds for this. So this paper is one such in this field of work. So now we have at IMSc work happening in algebra and computation, in identity testing, as well as in proof complexity. And of course, Boolean complexity is something that is always there at the back of our heads because I think complexity theory cannot escape that, and it comes from there. Small space classes is something that a lot of work here started with that, and maybe right now actively we are not working on that, but it is not at all inconceivable that some of us may return to that work soon. What about the future? Well, the tools from computational complexity, we expect that they have helped us to understand efficient computation in many different forms, in many different models of computation. And we expect that this will continue. As forms of computation in the real world change, the models, the abstract formalisms that we deal with will also evolve, and we will be able to analyze better and better what this computation does. And we certainly hope that the group at IMSc will, even though the members of the group will change, we hope that the group will continue to be active and will continue to be an integral part of this endeavor worldwide. Okay, with that I'll stop here. Thank you.